Hello, everyone, and thanks for tuning in. I'm Brian Miller, and I'll be presenting on work that I did with Leonardo Frid to dynamically link agent-based and state-and-transition simulation models. First, a little bit of background on each of these approaches. So state-and-transition simulation models are stochastic simulations with two basic inputs and two basic outputs. So the inputs are the area of a landscape in each state class at some starting point. And then the transition probabilities are targets that dictate if a given patch on that landscape will transition from one state class to another. And the outputs are the area in each state class over time and the area transitioned over time. In other words, these models can project vegetation dynamics, and importantly, they can do so with estimates of uncertainty. Now, one limitation of these models has been that they can't represent individual agents moving around a landscape and making individual decisions and actions that affect the landscape. And this is really the strength of agent-based models, which have three fundamental components: agents, an environment, and rules that dictate how they interact. So agents are quite flexible and can be any sort of autonomous unit that represent an individual or a collective entity. So this could be things like bison, livestock, people, even institutions or viruses. And these agents then operate according to decision rules that dictate their mobility, their ability to sense the environment around them. And these agents can even adapt or learn from past experiences from interacting with each other and with their environment. So recognizing the complementarities of these two approaches, we sought to link them together using a proof of concept case study focused on a portion of Badlands National Park in southwest South Dakota. Our state and transition simulation model is a simplified version of a model that we published in 2017 in Ecosphere. And this model provides estimates of vegetation production, biomass, and composition. And although it does have the grazing preferences and grazing effects of bison, it does not include bison movement around the landscape. So we developed an agent-based model that includes bison that move around the same landscape, and they accumulate thirst and make movement decisions based on their forage requirements and levels of thirst. And these foraging decisions then affect the vegetation in their environment. The vegetation portion of this model is fairly simple. It has primary production and decomposition rates that match the state and transition simulation, but it has static vegetation composition. And here's just a visual depiction of what I was describing on the previous slide, where the green boxes are the patch or grid cell level procedures, and the blue boxes are the agent or bison level procedures. And any one of these boxes has some more complexity in terms of the algorithms and things that dictate something like an individual bison's movement decision, but this gives you an overview of how the model works. Now, when we link this to the state and transition simulation model, we were able to then update the vegetation composition by passing information from the agent-based model to the state and transition simulation, indicating where bison had grazed, and then the state and transition simulation could update the state classes and grazing preferences and pass those back to the agent-based model. So to give you a general sense of how we did this, we used three software platforms: STSim, R, and NetLogo. R is really the intermediary here. We used it through the RSynchroSim and RNetLogo packages to drive both STSim, the state and transition simulation modeling platform, and NetLogo, the agent-based modeling platform. So we use R to initialize STSim, run it for a time step, and then importantly, we developed the capacity to actually pause the model run and not stop it completely, but just pause it so that we could pull out the relevant spatial data and convert it to a format that NetLogo could recognize. In our case, we were pulling out a raster of state classes. Once we imported those data to NetLogo and updated the patch values, we then ran NetLogo for a time step, paused it, and extracted the relevant spatial data and converted it to a format that STSim could read. In this case, it was the locations of grazing transitions and how much biomass was removed through those grazing transitions. We could then import those rasters to STSim, update the patch values, run STSim for a time step, and pause it again. And then we just repeated these steps as many times as needed to meet our full model run time and the number of iterations that we desired. So what were the practical implications of doing this? Well, we can see this when we look at things like the average annual probability of grazing on this landscape and comparing the different types of model runs. So here I'm showing output for what we call heavy and normal grazing transitions for the state and transition simulation model running just on its own. And you can see that the spatial pattern is essentially random. Now, when we look at the agent-based modeling output, there's much more obvious spatial patterning. And what this is showing is clustering of grazing events around water sources. And we see a similar pattern with the coupled model runs, but there are some slight differences, and these differences become more apparent when we compare through simple subtraction of the coupled and agent-based modeling runs. And what we see is that through the coupled model runs, we get a bit more dispersion in those grazing events. And this is because in the coupled runs, of course, the vegetation composition is being updated. So as grazers are concentrated around water sources, that grazing is impacting the type of vegetation that's there, and grazers have preferences. And so as they change the vegetation around them, there's a feedback that causes them to move to other patches to find the most desirable grass. Now, we also see important differences when we look at the time series of composition. So here's a sample of a couple of different state classes comparing the state and transition simulation model and the coupled model output. I'm not showing agent-based model output because those results are static through time. So to conclude, it's now possible to dynamically link agent-based and state and transition simulation models. And we're going to make the case study models as well as the R code publicly available once we have a publication accepted. More generally, this coupled modeling approach has a number of benefits. It minimizes assumptions, allows us to get closer to first principles of things like bison movement and grazing patterns. It increases the temporal resolution of agent-environment interactions that are available in SDSIM through that partnership with the agent-based model. And as a result, it generates more realistic spatiotemporal patterns, which I think has important scientific and management implications. And finally, it streamlines the handling of model inputs and outputs, which is really useful for automating our workflows, allowing multiprocessing, creating a record of the model inputs, and then ultimately facilitating the ways that we explore the outputs. So with that, I'll just quickly thank our funding source, the North Central Climate Adaptation Science Center, others at ApexRMS who provided ideas and programming support, and then also Tyler Beaton who provided sort of the seed for our agent-based model. And I'd also like to thank you for listening, and yeah, I look forward to receiving your questions.